today we'll be evaluating definite integrals using Riemann sums. So the Riemann sum is equivalent to the integral from a to b, or b to a, whatever, of f of x dx, and it is the limit as n approaches positive infinity of the sum from I equals 1 to n of f of xi times delta x. So over to the right here, we have delta x equals b minus a over n. This is because b, which is 5, I just drew a little mini graph just to show you what I mean by b minus a over n. Let's just say you're taking the integral of this little curve here from 0 to 5. B would be 5 and a would be 0. The reason why you subtract them like this is because 5 minus 0 is 5. That is the magnitude of the whole delta x's summed together, and you divide it by n because that's how many little intervals of the rectangles that you make, or whatever you want to make, trapezoidal rule, like that. So that is 1, 2, 3, 4, 5 n intervals, so n equals 5, and b minus a equals 5, so 5 divided by 5 is just 1. So in this case, this little mini graph, delta x would equal 1 over n. Or no, it would equal 1, but in this case, when you just take the definite integral of something, you won't know how many intervals of it because you're approximating the integral. So you're trying to get the delta x as small as possible, so an infinite amount of delta x's. So therefore, you don't really know what n is. That's why we take the limit of it as n approaches infinity. So we'll cross that out. So in this case, I have an example from the integral from 2 to 3 of x squared minus 1 dx. So when you have this, you will x sub I equals, over here, summation properties, x sub I equals a, which is 2, plus delta x times I. So delta x is right here, b minus a over n. b minus a, 3 minus 2 over n, so that's just 1 over n. So delta x equals 1 over n. So we have that part, and then now we need to find x sub I, which is 2 plus 3 minus 2 over n times I, because we know what a is, it's just 2, and then delta x, we already know what that is, it's 1 over n, so 2 plus 1, or it'd be 1 over n times I, so I over n, so x sub I equals 2 plus I over n. Now, in the sum, we have to find the function of x sub I. So therefore, we have to plug this in for all the x's in this function. So x squared, that'd be 2 plus I over n, all squared, right over here. And then minus 1. There's no x's in 1, so you just leave it minus 1, which equals f of the function of x sub I. So now you have that, and now you have delta x also. So now it's time to find the sum. So in this sum, n is a constant because we're summing up all the i's. So it acts as a constant. And over here, we have the sum as I equals 1 to n of k, which is a constant, equals k times n. So over here, when we plug all this in, and since it's all multiplied by 1 over n because that's what delta x equals, and in the Riemann sum right here, it's all multiplied by delta x. So this simplifies to 4 over n plus 4i over n squared plus I squared over n cubed. So when we find the sum of all of those, we can find the sum individually. So the limit as n approaches infinity of the sum as I equals 1 to n from 4 over n plus the sum as I equals n and so on equals the limit as n approaches infinity of 4 over n, which is 4 over n, so 4 over n, which is just a constant because we're not dealing with n yet, not until we take the limit. So that's just the same thing as saying 4 over n times 1, and 1 would be that constant k that we're talking about. So we can put 4 over n on the outside of the sum, so 4 over n times the sum of 1 when there's not even I, which is just k, is 1 times n, which is just n. So that's how we get the 4 over n times n, which already we can just cross those out because they cancel out. So we're left with 4. Now for the next one, we'll change colors, getting bored of blue. Okay, so the sum as I equals 1 of n of 4i over n squared, we can take out 4 over n squared because we're not dealing with those, just the I. So 4 over n squared right here, and then times n times the quantity of n plus 1 all over 2. That's the sum of I, and we have that over here, that when you take the sum of I from I equals 1 to n, you get n times n plus 1 over 2. So now we have 4 over n squared times n to the n times the quantity of n plus 1 over 2. So that's how we get this. And now we're left with the sum of, from I equals 1 to n, of I squared over n cubed. N cubed we can take out of the sum, so 1 over n cubed times, and then this part right here comes from this property right here. When you take the sum of I squared of I equals 1 to n equals n times the quantity of n plus 1 times the quantity of 2n plus 1 all over 6, which is a pretty messy problem, but we'll get through it. So, and since we're taking the limit as n approaches infinity from these 3 sections, we just have to evaluate the ratio of the numerator to the denominator of the highest powers. So 4, that leaves the same because there's no n in 4, so that's just going to stay the same. So when we bring this down, we're going to get, bring it over here, and we'll go in pink, and we'll go limit as n approaches positive infinity of 4 plus, alright, so n times n plus 1 is just n squared plus n squared plus n, and looks like a 2. Okay, so all over n squared, so we can get rid of this n right here because that's not going to matter, because n squared and n squared are both the highest powers in the numerator and the denominator. So the ratio is 4n squared to n squared. Since they're the same, it's just going to be 4 over 1 because it's n squared equals 1n squared. So 4n squared over 1n squared is just 4 over 1. So that's going to be, since n squareds cancel out when they go to infinity, because infinity squared is a lot larger than just infinity, because that's why we get rid of the n. And and there's also a 2 over here, so that's also in the denominator. So 4 over 2 n squared, but there's also n squared, so the n squareds cancel out. So you're left with the ratio of 4 over 2, which is just 2. So now we have that. Now we've taken care of these. And now we just need to figure out the last one. So we know when we multiply all of these, when you first distribute the n to the n plus 1 and then that to the 2n plus 1, the highest possible power we're going to get is going to be a power of n cubed. Because n times 2n, which is the greatest powers in each of these 3 sections, the highest power will be 3n squared. So all the others won't matter. So that's why it'll be, so 2n cubed plus whatever, which won't matter because infinity cubed is way bigger than any of the other n squareds or n's or ones, whatever. So it'll be 2n cubed over 6n cubed. So the n cubes cancel out. So we'll be left with 2 over 6, which is the ratio between the numerator and the denominator, which 2 divided by 6 is just 1/3. So plus 1/3. And now you have evaluated it, because when we evaluated n to positive infinity, all those n squareds over n squareds cancel out because anything divided by itself is just 1. So really, it's 4 times 1 plus 2 times 1 plus 1/3 times 1, but we don't have to write that. So we can cross out this limit because it no longer matters since we just have constants. And to change all these to 1/3 so we can have an easy fraction, 4 is equivalent to 12/3. Oh no, change a different color. Getting bored too quickly. Alright, here we go. So 12/3 plus 2 is the same as just 6/3. And 1/3 is just 1/3. 12 plus 6 plus 1. We'll write this in white. So 12 plus 6 is 18, plus 1 is 19. Oh, whoops. I wrote 7. There we go. Okay, so 12 plus 6 is 18, plus 1 is 19, and it turns out to be 19/3. And if you want to check this out, if you do the antiderivative of x squared minus 1, you'll also get 19/3, hopefully. So you'll get x squared, antiderivative of that is just x cubed over 3. Plus or minus the antiderivative of -1 is just negative x. All from 2 to 3. Add 3, x cubed, 3 cubed is 27, divided by 3 is just 9, and minus 3, so 9 minus 3 is 6. 2 cubed is 8, 8 over 3 is 8/3, 8/3 minus 2, 2 is the same as 6/3, so 8/3 minus 6/3 is 2/3, minus 2/3, here we go, here it comes, and, oh, what do we have here? So when you take that, this is an approximation, so this is probably, so 5 equals 5 1/3, which is 16/3. I have to figure out what went wrong. 4/3 is 12/3, yup. 6/3. What am I missing here? 4, that's 4, that's 2, and that's 2 over 6, 1/3. Alright, well, calculating definite integrals is an approximation, so that is why it will be off a little. I mean, maybe I made a mistake, but that's the process you have to do to find the Riemann sum. So whether I made a mistake or not, it's still an approximation. So 19/3 is somewhat close to 16/3. So that, yeah. So these are the properties you'll need to find the Riemann sum. So whether I messed up or not in this tedious process, that's how you evaluate it, whether I got it right or wrong. So